While a smart transportation system may involve several network components, this talk will concentrate on the access aspect of the communication in such a network. Communication links between entities among and in between vehicles, pedestrians, infrastructure pose different challenges in terms of latency and reliability. This talk will look at the current state of research and standardization with respect to these different communication needs. I think ITS is a very hot topic in the country right now. A lot of cities or municipalities are dabbling with ITS implementations. So this topic and this talk is very timely. Even last webinar we organized with a London-based consortium on intelligent transport system known as One Transport. So today we have an opportunity to listen from an Indian point of view. Today we have Dr. Puneet Rathod, who is Senior Wireless Technologist with the Next Generation and Standards Group of Intel. And few words about him. Dr. Puneet is a Senior Wireless Technologist with Intel, where he is working on prototyping and pathfinding activities. Prior to this, he worked at IIT Bombay representing the research group at 3GPP ran 2 groups. He has dabbled with entrepreneurship for a brief time in his startup on emergency communications. He has done his PhD from IIT Bombay. He has been working in the wireless communication, wireless networking domain, specifically on resource scheduling, network protocols, test beds, and performance analysis for more than a decade. So without further ado, I would like to give the floor to Dr. Puneet. But before that, a small housekeeping announcement about the questions and the flow of this webinar. So Dr. Puneet would be making the presentation now, and you might ask your questions using the questions tab, and he will be taking up the questions once he has finished with his presentation. So over to you, Dr. Puneet. I hope you can start now. Can you hear me? Can you confirm?
Yes, I can hear you. So just confirm my audio and then we can go ahead.
Yeah. So you are good, and I will go on mute, and over to you.
Okay. Thank you, Sachin, for the kind introduction, and good afternoon, everyone, and good morning, everyone joining from Europe, and good afternoon for those joining from India. So today I'm going to talk about vehicular communications in the context of intelligent transport. The main focus of this would be to look at this from the perspective of different requirements and the primary use cases for vehicular communications in the context of intelligent transport. And when we look at this, we will also look at it from the radio access point of view, which is the last link in the communication. As Sachin was also mentioning about the previous webinar, that particular webinar discussed about all the applications and different marketplace and data exchange semantics of intelligent transport. This talk will be a complement to whatever was discussed in the previous webinar. So a brief overview of how we will be going through in the rest of this talk. We start with the requirements and primary use cases. Then we will take a look at how are the technologies evolving to address these use cases. And when we try to look at this, mainly we will be looking at how are the standards leveraging existing technologies for data communications and transforming themselves into a vehicular communication standard. We will also follow up with how does this connect to a 5G vehicular requirement, and what lies in the future for standardization of such vehicular communications. And just a very quick overview on how the ecosystem for vehicular communication is taking shape. In terms of the scope, so as I was mentioning, we will be taking a look at the radio side of the vehicular standards, and the use cases and the interaction with the standards, and briefly touching upon IEEE and 3GPP standards existing on this domain. We will not be touching upon the service layer and the application layer aspects, and we won't be looking at different interfaces for data exchange and the data exchange semantics. And we will also not try to delve into a competitive analysis of IEEE standards versus 3GPP standards addressing the same use cases. Both of these different standards will have their pros and cons depending on the use case, the standard readiness, the prototyping, and the market readiness. So a competitive analysis will be out of scope for this particular talk. So before we dive into this entire talk, let us quickly take a look at autonomous driving as an example. This will help us relate to a lot of examples that will come later in this talk. From an intelligent transport point of view, there are several communication needs that autonomous driving may require. And when we talk of autonomous driving, it does not essentially mean a fully hands-off driving all the time. There are several different levels as the Society of Automotive Engineers define, and the level 5 is what is the first thing that comes to our mind, which is a fully automated drive without any human interaction, and the car is capable of doing everything on its own, to the point that even a steering wheel is optional. So that's the level 5. That's the ultimate automation in driving. And below that, there are several other levels of autonomous driving, which may get classified as assisted driving or advanced assistance to driving, and various other different labels that get assigned to it. And during this talk, all of these use cases and requirements that we come across may fall into one or more of these categories below the level 5. And the level 5 and level 4, they are the more advanced levels of autonomous driving, which may need much higher demand, which may pose much higher demands on the vehicular standards in terms of latencies, data rates, and other parts. So this is just to give that quick overview of what do we mean by smart vehicles or an autonomous vehicle and the different levels, so that we can relate to this when we come across different requirement use cases. So with this quick introduction, let us look at the high-level applications and requirements that come up. So one of the primary usage of any sort of intelligent transport systems is safety, and all across the globe there are several statistics that show one of the major causes of deaths on the roads is highways and accidents, and that is one of the main starting applications for intelligent transport systems. And that is so the first one is safety and automated driving and advanced driver assistance systems. These are the set of applications that require high reliability and low latency, and all of this communication will be happening when the vehicles are traveling at high speeds. A few examples, we'll be looking at these examples in a little bit more descriptive fashion when we come to specific technologies, but to give a feel of exactly what these examples look like. So when we say forward collision warning system, what it means is that if there is a car that is following, so the moment the distance between two cars reduces below a safe limit, then the following car can get an advanced warning, and then the level of automation, the car can decide what is the corrective action that can be taken. Will it slow down? Will it give a warning to the user? So if it is higher level of automation, it will take a corrective action in an automated manner. If it is lower level of automation, then it will give a warning to the user, and the user needs to take control. So 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 if this communication is possible and exists, then this warning can be addressed by either the user or the automated system. If you look at one more example, like for example, control loss warning. Control loss warning is also what we see in sort of a semi-automated driving scenarios, where the user is supposed to be alert of the vehicle, and it is not a fully automated driving, but the user is supposed to be alert. And if the user loses control, or the user is not alert, and the user is distracted, or watching a movie, like what we saw with one of the examples with the Tesla car crash, where the user who was driving the vehicle, he was too confident about the autonomous driving abilities of the vehicle, and then was watching a movie. And so this loss of control warning is also a warning to the other vehicles on the road when there is loss of control by one of these automated cars or assisted driver cars. The second use case or the second major application category is situational awareness. From a situational awareness, what it means is that there could be hazardous road conditions, oil slips, snow on the roads, or potholes, puddles, and several other examples of that. These will also require very stringent reliability considerations, but at the same time, these are much far away from the action. These are not vehicles which are very close to each other when they are traveling. So the latency requirements are slightly relaxed, but the other conditions remain the same. If you look at further high-level application categories, there are mobility services, which include automated parking, toll services, traffic advisory, dynamic ride sharing. For these applications, the latency considerations are further relaxed. Even the reliability considerations are further relaxed, and there are security and confidentiality requirements that kick in. And the final one is auxiliary and comfort use cases, where as the vehicles start becoming more and more autonomous, then the passengers in the car can be free to consume more and more data. And so these take part in terms of infotainment, local services, fleet management, and all the other services. So from these all different broad categories, there are two main kinds of messages that are defined in the dedicated short range communications specification as an umbrella set of standards. The first one is periodic cooperative awareness messages, CAM. So these kind of messages are periodic in nature, 10 messages every second, 100 messages every second. So there is a periodicity to the message. These kind of messages are mostly about the status of the vehicle. By status, it would mean the speed, the direction, and any other condition of the vehicle that needs to be announced on a periodic manner to the neighborhood, and it is a broadcast to the immediate neighborhood. Then there is an event-driven decentralized notification message. This is multi-hop, and it is based on a trigger. The trigger could be something happened to the vehicle, there is an accident, a collision has happened. So there could be an event which will trigger this message, and this message can propagate more than one hop from the source of the message. If you look at further examples of exactly what these are, so if you look at the CAM messages, there could be emergency vehicle warning. So if an ambulance is coming along the path, the ambulance can keep broadcasting the route it is taking, and all the vehicles on that path can then be aware that an ambulance is approaching, and then they can clear, and they can probably get a notification to clear up the path. Collision risk warning, slow vehicle indication, motorcycle approaching. There are several such examples which are periodic in nature, and the vehicle which is every vehicle will be sending these messages on a periodic basis. So how it would be happening is, if there is an intersection assistance use case, then a periodic broadcast of the location, direction, and speed will be sent by the vehicle, the source, or the roadside unit, which could be an infrastructure device like a street lamp pole, and the message is sent to the immediate neighborhood, which is supposed to deal with this. And for the decentralized, as I was saying, these are trigger-based messages, and based on a trigger, these messages will remain alive till such time the terminating condition is detected. So if there's a stationary vehicle which has met with an accident, then an emergency call will be triggered, and till the vehicle is cleared from the location, this message will continue to be triggered. And different use cases may have different latency requirements. For example, roadwork warning. So now the roadwork warning, so the origin of this message is not a vehicle, but this is some fixed infrastructure on the side of the road where this road repair is taking place. And till such time the road repair continues to take place, this message may keep getting broadcast, and basically once the repair is done, this message can be ended. So, and depending on these different use cases, the latencies are either there is more tolerance on the latency or less tolerance on the latency. Now, so with this is the set of high-level use cases and all the different kind of scenarios in which these autonomous or semi-autonomous messages may be required by an intelligent transport system. I will also touch upon the network part of it, because this is still a very high-level introduction of these use cases. When we look at the different technologies, I will delve into a little bit more detail on further classifications of these message exchanges. So now let us take a look at all of these different requirements that are showing up for vehicular communications, and how are the standards adapted to satisfy these. The first of these is IEEE based standards based on Ethernet Open 11. Ethernet Open 11 is also popularly known as Wi-Fi, that we are aware in our daily lives. So the basic Wi-Fi network is an access point which we have in our home, the home Wi-Fi router. So that's the access point which will keep broadcasting the SSID or the name of the Wi-Fi network. And all of these Wi-Fi clients or the Wi-Fi STAs, Wi-Fi stations, will detect, will give a password and then associate with this access point. And this network is, from a Wi-Fi standard point of view, it's called Infrastructure Base Station Service Set. So that's the BSS. In an enterprise setting, for example, a coffee shop, an airport, or an office, or a campus, or maybe even a public Wi-Fi system, more than one Wi-Fi access point can exist, and all of these Wi-Fi access points are connected via a distribution service. So now there is a single Wi-Fi network spread across several access points, and all of these Wi-Fi clients can roam from one access point network to the other access point network, and this becomes an extended base station service set. Both of these still continue to have this Wi-Fi network to which a client needs to associate by providing a security key. One of the other examples of Wi-Fi standards was the ad hoc mode. In the ad hoc mode, there is no access point. Everybody is a Wi-Fi station, and the Wi-Fi stations can talk to each other. There have been more than one flavors to this. So the ad hoc mode is the most base version of it, and beyond that, there have been different enhancements to the Wi-Fi specifications in terms of the NAN mode, which is the neighborhood awareness networking, and also called as Wi-Fi aware. Then there is WideEye, and several other enhancements, which again depend on establishment of this independent BSS. So this again means that any station that needs to talk to a different station needs to first establish what is the name of the network, and then they can talk. Now, if we try to imagine how will this work, the moment we talk about vehicles. Now, if a vehicle has one of these Wi-Fi based radios, and the neighboring vehicle, so a vehicle manufactured by Suzuki needs to talk to a vehicle manufactured by Toyota, and both of them manufactured in probably different states and different Wi-Fi modules. They cannot, and probably traveling 80 kilometers per hour. They cannot wait for detecting the Wi-Fi channel, establishing the base station set, establishing all the security keys, and then sending the first message out. By the time it will be already time for an accident, or the collision warning is too late. So the 802.11 standards that were adapted to address this vehicular networks was the primary thing that was established was communication outside the context of a BSS, which is OCB. So that's also the name of the Wi-Fi standard 802.11p that addresses this. So either it is 802.11p or 802.11 OCB. So the key thing that is established here is that the station can talk. A station does not belong to any of the BSS. The station does not even need to establish a BSS before communicating. And whenever a station is sending any message in a broadcast fashion, it is setting the BSS ID in the packet to a wildcard entry and wildcard value, and then it is just broadcasting. Now, so this what this does is this establishes the physical layer, which is very similar to the Wi-Fi protocol. It also establishes the MAC layer, which is again very similar to the Wi-Fi protocol. However, with the small change that it does not need to establish the BSS. In addition to all of this, to enable all the vehicular communication, there is another set of IEEE standards called Wireless Access for Vehicular Environment, WAVE, which is also the series 1609. And so this entire series gives us a whole set of different standards, right from the higher MAC, which is the medium access control and multi-channel operation. When all of this vehicular communication is happening, there is absolutely no time for the Wi-Fi station to scan and check what is the channel on which the communication is happening. So the multi-channel operations of WAVE 1609 series establishes a set of control channels and shared channels where all of this communication can happen. It also establishes a set of short message protocols and a rate control on how many messages should go, how frequently, and all of these semantics are established by the 1609 series standards. On the top, it still relies on TCP/IP and the other standard IP stack. 1609 also establishes a set of security features and some basic security and the entire security feature set, which is over and above the Wi-Fi 802.11p. So it kind of replaces the Wi-Fi security, because now there is no longer a Wi-Fi authentication taking place, but all of that is taken care of by 1609. And when we look at, so OCB was one major change from Wi-Fi to 802.11p. There is one more change that is happening in the Wi-Fi standards to go from standard Wi-Fi to a vehicular Wi-Fi. And that particular change is to do with how the physical layer behaves. And so this slide is just providing a quick summary of exactly where the change is. So if you look at the first two rows, so the total number of subcarriers. So when we look at a standard Wi-Fi signal that we can see in our homes and any other hotspot, it's a 20 megahertz bandwidth of OFDM bandwidth. And that entire OFDM carrier has 64 subcarriers. Each one of those 64 subcarriers is 312.5 kilohertz wide, or 0.32 312 megahertz. So when it moves from, and this entire Wi-Fi was designed as a philosophy, it was designed to be indoors. And when it and all of this communication from a vehicle point of view is supposed to be outdoors. So when we take the Wi-Fi protocol and make it behave outdoors, to make it more robust, the bandwidth is reduced to half, and the carrier spacing is also reduced to half. And with this, the symbol duration increases, and also and as a result, also it gets more flexibility in adding more cyclic prefix, and the inter-symbol interference can be much better, providing it better resilience to outdoor operations. So this is the other key change coming from standard Wi-Fi to Ethernet 2.11p. Now let us also look at how is the cellular technology evolving from the LTE world. So this is how the Wi-Fi world tried to address this vehicular standards. If you look at the cellular world, there are, from Wi-Fi standards point of view, every node, it's a very democratic system, and every device is almost equal. And the way they access the channel, everybody accesses the channel in the same way. And there is no centralized scheduling. The access point is as much likely to get access to the channel as the client. So in an LTE world, the base station is the master of the channel, and the base station assigns resources to the client devices, and the client devices can transmit only when the base station assigns these resources. And because of this, there are these different communication methods that get defined, which is either it is a vehicle to vehicle, it is a vehicle to infrastructure, vehicle to pedestrian, and different communication links. So this is the device to device part of it, where there is a vehicle to vehicle or a vehicle to infrastructure or pedestrian communication. Then there is also a device to cell tower communication, which could also mean that instead of a cell tower, it is a roadside unit. So it could be a street pole, it could be some other sensor on the side of the network on the road, or any other roadside unit. And the final set of kind of communication is device to network, which is by network, it is a much broader term. It could mean that the destination of the communication could also be somewhere in the cloud, in the data center, and it could be sending measurements from this situational awareness on the road to the cloud. So which could mean that there is a central repository of all of this situational awareness of how the traffic is in a particular area from all the vehicular measurements in that zone. So that is a device to network. When we look at all of these, how 3GPP deals with this in terms of standardizing is it tries to look at all the stage 1 requirements or English language requirements in terms of what are the different use cases and what are the different key performance indicators these different use cases generate. And then there is a single unified technology that is built to address this wide variety of use cases. So we looked at like a couple of them sometime earlier in this talk, and we can and these are, so those were more generic, looking at how is vehicular communications and how are the different vehicular communication requirements showing up in general. And these are the use cases that 3GPP took into account in specific before standardizing the V2X or vehicle to vehicle, vehicle to infrastructure, or vehicle to pedestrian. So all of these 27 different requirements were considered by 3GPP more than a year ago, when all of the standardization of vehicle communication was taking place. And a lot of these are coming from the same set of requirements like forward collision warning, control loss. And then there are additional requirements. For example, if you look at number 11, which is V2X message transfer under MNO control. Now this is something which is unique, which also allows the possibility. So MNO here is the mobile network operator, and it also allows the possibility that a vehicle, so if two vehicles are within the range of the network infrastructure, then these two vehicles can talk to each other through the base station. So these need not be talking only directly to each other, but there is also a possibility that opens up where they can talk to each other via the network. And this is where there is an additional flexibility that the cellular communication provides as a part of all of this, as a part of the standardization. As a quick example, if we look at the different speeds, so all of these 27 examples, 27 use cases, and the different key performance indicators that they pose on the standards is available in this 3GPP Technical Report 22885. And if you look at all of these different speeds at which the different vehicles can be traveling, all of these different speed pose certain kind of constraint on the tolerable latency, and not everything is a direct correlation. For example, if you look at item number 3 here, it's an autobahn, very well paved motorway and very high speeds. And when the requirement comes from this, so the relative speed between two vehicles is the same as the absolute speed of the vehicle, which is there is very less likelihood of vehicles in the opposite direction to be communicating, and it's more critical for the vehicle on the same side of the road to be communicating with each other. Whereas in a campus or a shopping area or an urban intersection, it is also possible that the vehicles are coming in opposite directions and then they can still be talking. So although the absolute speed is 50 kilometers per hour, but the relative speed could be twice of it. And so that is depending on different use cases, the requirements change, and these, looking at these requirements, then the standards are addressing these different needs. And when we look at 3GPP, from a network point of view, on the left hand side is how a typical LTE network looks like. There is a base station tower, and there is a wireless link between the tower and the user. In release 12 of 3GPP, there was an enhancement brought in for public safety use cases, which is mostly emergency communication systems, that allowed two users to talk to each other, both in the coverage of a base station or even when they are outside the coverage of a base station. And this was primarily looking at emergency public safety use cases. And this lays the foundation of, just like Wi-Fi ad hoc mode allowed for the basic foundation for vehicular services, this D2D communication laid the basic foundation to allow for vehicular communication standards within 3GPP. So, so on the bottom part, there is the basic architecture of how the 3GPP network looks like. On the left-hand side is the user, and then there is a base station, which is the U-turn block. And the second block is the packet core, which is like a data center wherever the operator core network is there. Maybe 3 or 4 core networks for an entire operator in the entire country. So that is the kind of scale. And then the communication from the user is going to the internet through all of these servers from the core network. Going from there to device-to-device communication enablement, any user who wants to talk to a different user in a D2D paradigm, there is a proximity services application that is available, which can allow the two users to talk to each other through this PC5 link. And this PC5 link can exist even when the users are outside the coverage of the entire network. So that is the basic foundation based on which vehicular networks standards will evolve within 3GPP. So so this is the journey where release 12 specified how D2D can operate for public safety. That particular standard specified device discovery and a reliable one-to-many communication, which is a broadcast communication. So a user, it is like a walkie-talkie kind of communication. A user will transmit a message and it will be broadcast to the entire neighboring vicinity. And if we imagine from how all the other examples that we have seen so far, it is very similar to this CAM broadcast message, that a periodic broadcast message can go through this. release 13 enhanced this entire D2D standards, providing more flexible discovery of the users. So in release 12, the device discovery was limited only when, so it was possible to discover the devices only when the users are inside the base station network coverage. In release 13, more flexible discovery and a private restricted discovery was also possible even when the users were outside the coverage of the network. And release 14, which just got standardized and the specification became available March 2017, that is when the first set of standards for vehicular communications were available. What this provided was, in addition to the D2D communications, there was multi-hop and other specific enhancements for vehicle to vehicle and vehicle to infrastructure and vehicle to pedestrian. So all of these different enhancements were made. So exactly what are these? So we'll just take a quick look at how these look like from the network point of view. So V2X has two different modes of transmission. The first is a direct mode of communication, which is on the left-hand side, where PC-PHY interface provides a device-to-device kind of communication. These are latency-sensitive use cases which will give speed, location, direction, and these kind of information. This will operate on the global ITS band on 5.9 gigahertz and independent of a cellular network. So none of the licensed frequency bands are required for this to operate. The second set of communication that is enabled by V2X standard is that all of this communication can also happen on the cellular network. So the cellular network can facilitate this communication, and in the absence of the 5.9 gigahertz ITS band, this communication can still happen. It can all, so these are the use cases where they are latency tolerant and traffic condition, road hazard warning, all of these kind of situational awareness delay tolerant messages can be transmitted using the second kind of transmission mode. There is also just like the D2D support of release 12 and 13, there is both in coverage and out of coverage mode. When we look at in coverage mode, it allows for different frequencies of operation. So all of these different cars that we see. So it could be 3 different operators, maybe Vodafone and Airtel and Reliance Jio, all of these different operators providing services to different vehicles using their own frequency bands. That is on the licensed frequency. It is also possible that all the V2V, all the black color arrows here, they can be providing communication on the unlicensed 5.9 gigahertz frequency. So both these modes are possible when the vehicles are in coverage. In the out of coverage, they are just communicating on a shared direct communication on PC5. So in summary, all of these 3 different use cases, V2V, V2P, and V2I, they can both talk directly to each other and through the network. In terms of the stack, the V2V stack is specifying majority of the lower layer protocols, reusing most of the 3GPP existing semantics, right from the physical layer to the medium access and the radio link and packet data protocols. It is also reusing a lot of the D2D proximity services signaling. And beyond that, for all the application layer services, it is leveraging all the other standards that have been created from IEEE, ETSI, and ISO for security, message transfer, TCP/IP, transport, and all others. So there is a lot of reuse of the application layer stack, and the radio level stack is provided by the 3GPP vehicular standards. So from that perspective, both of these IEEE and 3GPP standards, both of them provide this lower layer communication message, and then there is a lot of scope for the reuse of this application layer stack from the other standards. So with this we are at the current state. So this is the V2X standard that is standardized as of March 2017. Starting now, 3GPP is also looking at how does 5G look at all of these different use cases, and that is where a lot of these fully autonomous and advanced autonomous driving use cases come in. And 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 if you look at a few of these examples, so there are a total of 25 different use cases that 3GPP is considering. Again, these are available in 22.886. There is a small typo here. So these are available in 22.886, and just to take a look at a couple of them. One of them is the first one, which is support for vehicle platooning. So by platooning, it means that more than one vehicle or more than one truck on a highway, they're traveling, and only the first truck is doing most of the driving intelligence, and all the trucks in which are following, it's kind of a train but on the road. And platooning is one of the main applications where from logistics and all the other use case point of view, it provides a lot of benefit in terms of fuel efficiency and minimizing a lot of minimizing losses and minimizing accidents on the road because of this because of the platooning and a cooperative driving. There is also as a result of this platooning, then there are related use cases that emerge. For example, if you look at use case number 17, so if there is a platoon of 5 trucks which is traveling on the road, and there is a slow vehicle which is in front, if they need to change the lane, while changing the lane, if the next lane is occupied and only one of the vehicles in the platoon can change the lane, then either the entire platoon needs to slow down or the platoon needs to brake, and then only 2 of them will change the lane. The others will, instead of being a follower, now it is a smaller platoon. So this is like a change of mode, and this is the kind of use case that emerges out of these. So out of all of these different 25 categories, 3GPP classifies them into 4 very broad categories, and these 4 broad categories are platooning, advanced driving, extended sensor, and remote driving. And these 4 categories, so out of the 25 use cases, they are distilled into 4 broad categories. And all of these 4 broad categories pose a few very specific but different requirements on the system. From a platooning point of view, there is very high data rate requirement where vehicles obtain information from the leading vehicle to manage the platoon. From an advanced driving point of view, this is about cooperating between the vehicles and getting a common perception of how the situation on the road is, and can the vehicle change lanes, can it be an assisted semi-automated overtake, and all of these different advanced driving use cases. Here latency is very crucial, reliability is very crucial, and at the same time data rate is high. Extended sensor is one of those use cases where there is a bulky vehicle in front, and it needs a situational awareness of exactly what lies ahead of that vehicle. And for example, we can consider a road without any divider in between, and if the vehicle on the back needs to take a decision whether to overtake or not. So this situational awareness from an extended sensor point of view to get a visual or an information whether this overtake decision can be taken or not. So again, here there is very high data rate requirement which is coming up. And finally, the remote driving use case where the control of or driving the vehicle is coming from a remote user. It's like a robot. So somebody else is driving the vehicle sitting at a data center. So here the reliability requirement is extremely high. So these are the different 5G use cases, and the standards are under development as we speak. So with this, we are at the end of how the standards ecosystem looks like, and how is the IEEE standards looking like, and how are the 3GPP standards looking like, and how do they relate to the use cases, and what are the major changes that have happened from the from the plain vanilla data communication stream to the vehicular communication standards in these two different kind of standards. From an ecosystem point of view, I'll just take 1 minute to quickly brief mention about a 5G Automotive Alliance, which is now formed, which is now represented with a wide cross-industry consortia, and this is helping in defining all of these realistic use cases from the 5G communication point of view for vehicles. 5GA is also now a market representation partner of 3GPP, and then it will also be taking all of the requirements from the end users and the entire ecosystem back to 3GPP for standardizing. And as we can see, it is very well and widely represented. So and this 5GA is also sending out periodic white papers on how does the ecosystem see the deployment of these different standards, and at least from there, from the point of view of 5GA, which is represented by all of these different vendors and ecosystem, the end users as well. So the initial phase, as envisioned and as realistically envisioned, is that initially there will be unlicensed ITS band 5.9 gigahertz vehicle to vehicle and vehicle to infrastructure communication, with the network backend being provided by road safety authorities or a centralized cloud which is available. And as the ecosystem matures further and further, more cellular based communication can be made available, and the network intelligence can also come closer, where the network front end can also provide these roadside units which can provide additional high latency sensitive application to be enabled. So that's the advanced phase which will follow once the ecosystem matures. So to wrap up, there are several use cases for V2X leading to an intelligent transport system enabler, and the 4G and the 5G evolutions are addressing these semi-autonomous to fully autonomous driving cases. And one of the primary usage of all of this is safety and reducing the accidents on the road and better management of the traffic on the road with all of this information. And there is a lot of reuse of existing technologies from the data communications technologies to this vehicular communication that leverage the economies of scale when these standards emerge. And with this, I'm at the end of my talk and I'm open to questions.
Thank you, Dr. Puneet. It was a wonderful presentation. I think the questions will start pouring now. There is already some question, that was asked by Mr. Vijay Madan that Jaita has posted, so you might already take it. And as they keep coming, I will keep assigning them to you. So can you see the questions tab? Can you confirm?
Yes, I can see the questions. Thank you.
Yeah. So please read out the question and the person who has asked the question, and you can read out then the answer. Thank you.
Got it. Okay. Thank you. So I'll go with the first question, which is how will the use case mixed mode of vehicle, autonomous and manual coexist? So so these are not strictly exclusive to each other, or these are not. This is not an either-or situation. So on the road there will be both legacy vehicles where there is absolutely no automation, and there will be vehicles with a high level of automation, and all the vehicular automation will be taking into account both pedestrians, motorcycles, bicycles, and any other non-automated driving. So at least my personal view would be that till a very long time there won't be a fully homogeneous, fully automated vehicle network. It will be a mix of both. I hope that is answering that question. I will go to the next question, which is in abroad you have 5.9 gigahertz to operate. Just wanted to know how do you operate the similar scenario in India? Okay, so with this, I think this is something that needs to be explored and studied, both from the national frequency allocation point of view and also coexistence point of view to whatever other technologies are occupying neighboring bands. And as it is very much valid for every other technology, it will be very similar for this case as well, that to be able to leverage all the economies of scale, it will be very beneficial that that at least the same frequency band, if not the same frequency number, if the same frequency tuning range is available, it will be very, very beneficial for the ecosystem. The next question, I have a very generic question. What kind of deployment scenario you foresee in V2E and V2X infrastructure, which is citywide, statewide, or nationwide? How multiple technologies shall interplay, in particular license and license-free centric technologies and standards? Okay, so yeah, there's kind of a more generic question. Right now, from the perspective of India, I would imagine that it is very, very likely that with all the focus on smart cities, there could be some kind of a traffic monitoring or a traffic sensing. Those kind of use cases may show up first. Logistics is one more use case where a lot of businesses may be interested. So logistics related, vehicular tracking and vehicular, so all of those use cases may show up. And after these use cases show up, if we try to tie all of this with the previous webinar, which is how do these data streams, how do we make sense of all of these data streams coming from more than one sources, and we store them in a unified format and make it available to a wider innovation audience, and then what else can be done with that data? So that is what I would imagine from this. The next question is so in regard to radio link at 5.9 gigahertz, is it unlicensed? And can you share the data sheets for the radio link? And please confirm if the radio links are line of sight or non-line of sight. Can we use cellular frequencies at 2.3 gigahertz if the radio link is not technically feasible in metro areas at 5.9 gigahertz? Okay, so 5.9 gigahertz, yes, it is in most of the other countries where it is used, it is unlicensed. For the radio link, the standard is 802.11p, and all the other higher layer protocols is 1609 series. So these numbers are also there in the slide. So when the webinar is shared on the YouTube channel by Sachin, they should be available. And these communication are definitely line of sight because of the frequency of operation. 5.9 gigahertz is very sensitive to all kind of obstacle related losses. So this is with a very high likelihood it is line of sight. There is one question which asks what do you mean by hop? By hop, I mean one hop is from one device to the next device. One transmission is one hop. Now, which is imagine like a Chinese whispers. So the first person saying a message to the next person, that's one hop. The next person relaying the message further, that's the second hop. So that's what I mean by hop. Regarding the question on hop, that is in CAM. Okay, I think this is the. Okay, I think it was just a continuation of the question. So I'll go to the next one. Do you see a situation where there is lesser and lesser gap between MAC and the network layers? Perhaps we will have one single layer standard that handles infrastructure to the cloud communication. In a way, I believe that the MAC layer may still be very closely tied with the underlying technology. For example, the Wi-Fi or the or rather the 802.11p MAC layer continues to be random access. It will sense the channel and then transmit. It's a CSMS CA based MAC. All the V2X MAC is not CSMA based. Either it is semi-persistent scheduling or it is base station assisted scheduling. So the MAC layer is very closely tied to how the technology behaves. So at least I don't see the MAC being decoupled fully. Whether the MAC is unified with the higher layers, that is again from the higher layers. The higher layers are very use case specific, and the next set of higher layers specify all of these message semantics, and after the message semantics comes the applications. So from the MAC and higher, I think at least I believe that that partition may still continue to remain. The next question is, can 5G and Wi-Fi connection co-work in its ITS 5.9 gigahertz? Yes. So both V2X standards, at least in 3GPP V2X standards, there is definitely this has been a part of the standardization. This has been a part of the study and also the specification development, that how can they coexist. So this is definitely there. So if you look at the 3GPP standards, I can take a look, or maybe in the webinar and the first slide you have my email address. You can try and reach out to me. I can try and look up the specification numbers where V2X is specified. The next question is how to take care of lane driving issue in India if we need to introduce driverless cars. Yes, this is a much broader question. At least from the lane driving point of view, we may not have a lane driving as a direct perspective, but there could be a lot of other usages continue to remain. For example, road hazard warning, road repairs, traffic situational awareness, ambulance approach, a lot of other collision warnings, lot of other communication modes continue to remain valid. A fully autonomous driving, maybe right now inside of the city, it's a difficult ask. Maybe on like all of these new highways that are coming up, in the highway between Bombay and Pune, maybe in the highway between the Gurgaon highway, possibly. So all the freeways, which is Autobahn Germany, is one such highway where everybody follows the lane. Expressways, everybody almost follows the lane. So possibly those are situations where cruise control and semi and fully autonomous could be a possibility. I'll try to answer as many as possible. There are a few more, but how 3GPP standards for vehicle communication is different from 802.11p. Okay, so 3GPP standards, they derive from OFDMA and they derive mostly from SCFDMA, which is the 3GPP uplink from a device to the network. That is the base technology that it derives from. 802.11p derives from OFDM, which is the Wi-Fi technology, and both of them also differ in terms of the MAC. So 802.11p is CSMA based, and 3GPP can do both FDD and TDD in that. The next one is how do you handle the latencies when bandwidth is reduced and increase the symbol duration in 11p? Okay, so this was definitely a part of the design consideration, and latencies are met when so when the bandwidth is reduced, it does not it still makes available almost 25 Mbps of traffic still available for the transmit of data. And with short messages, if the amount of data to be transferred is not very high, .11p can still handle the latencies. So this is definitely a part of the design consideration when 11p was standardized. So most of the CAM messages which need a frequency of 10 messages per second, it is possible. I don't think I have time for more questions, Sachin.
So one possibility, Dr. Puneet, is that we can mail you the questions, right? And you may provide the answers and already your email is shared with the people. So that is one possibility. But if you have 5 more minutes, from our side, you are free to take up more questions.
Yeah, I don't mind.
Okay.
Okay. So so there are a few more. So can we use the existing channel models or needs to come up with new channel models for supporting this ecosystem? In terms of the channel model, I don't think that we will need a new channel model. Most of this has been under very active research for the last decade now. So in fact IEEE has like a specific conference dedicated only to vehicular communication. So in terms of the channel model, I think both the research and the industry ecosystem understands this channel quite well. So we may not need a new channel model for this. The next question is, in the use case, you talked about about 5 stages of fully automatic or semi-automatic. How do they coexist in the same scenario? Yeah, I think this was briefly touched upon by me in one of the earlier questions. I'll go to the next one, which is for V2V through base station. How are the latency requirements handled? Yes, so when the V2V communication happens via the base station, most of these communications are situational awareness and network to the cloud, vehicle to the cloud kind of communication. These are not heavily latency sensitive applications. So collision warning and very high latency sensitive applications will not be via the network. I believe this was also in one of my slides. Then how to prevent hackers sitting in a car by the side of the road from sending malicious packets to the car? Yes, so yeah, I believe this is one more aspect, at least on the security and other parts. This was not covered as a part of this, and maybe this can be a separate topic onto itself. At least this particular aspect was not in the scope of this. So I would leave it for further exploration. But of course, there are both from the 3GPP and the IEEE standards. Both of them do have the security layer as a part of this standards, and but I would not go into a lot of detail on exactly what are those, and it can be checked. The next question is, we think that the radio link has to be non-line of sight in metro environment. Yes, so this is definitely this is true, and this is not precluded. But then the moment there is non-line of sight, all of these standards, they do support blind junctions and all of these. So either there is a roadside unit or a multi-hop communication that will enable all of this. So a fully non-line of sight may require a different set of frequencies, which may or may not be feasible. So if at all there is a non-line of sight requirement, then more than one hop is also a possibility to reach that. But then it will not be a single hop communication, but more than one hop communication, and that can still address this requirement. And I believe I have the last question here, which is, can attenuation of signal be a problem in the V2V network? Yes, so attenuation is definitely something which is a direct consideration here, and that is also why both from the 3GPP and the IEEE standards point of view, the 3GPP tries to add one more license band frequency as an additional frequency available for the communication, and along with that there is also a multi-hop communication which can help in propagation of the network communication farther. And if both of these are not possible, then there is also a roadside unit which can be a part of the street pole or any other road infrastructure which can propagate the signal further.
So thank you for taking all the questions patiently, Dr. Puneet. You touched upon some very interesting topics during your presentation, I'm actually emailing your email ID to, I mean, not emailing, but sending by chat to anyone who has further questions to be asked, because Rahul was sending a message that he wants to ask you more questions on email. So I hope you can, reply to them as people ask you more questions. You talked about also 5G AA as a project. Coincidentally, we are in touch with 5G AA with Mr. Dino, who is working with the Secretariat, and they are also having some kind of a presentation on intelligent transport system. So in the following upcoming webinars, we might organize, also a session by 5G AA. Also, somebody talked about car security. So I was in my reading, I find out that the European body for security, ENISA, there's a car security expert group. So I've just posted that link also because they have come up with a report on that, on securing smart cars. So thank you again, Dr. Puneet, for taking out your time and educating all of us on what's happening in vehicle-to-vehicle domain. And I hope you also enjoyed it, and we look forward for future engagements with you. Thank you. Thank you, everyone.
Thank you.